Okay, next section, technical basics. Okay, broad sweeping generalisation. The universe is made up of matter, and that matter is made up of even smaller particles called atoms. They are electrically charged particles called protons and electrons and a few others. These particles give rise to electricity as we understand it, and obviously drive today's electronics, and that electronics that's used in amateur radio. So now it's the flow of these charged particles that we're interested in, and a good example is something like static electricity, where you rub two dissimilar materials together and suddenly you find you've got a charge when you step out of the car or whatever, and all of that sort of stuff. And another good example of static electricity is lightning flowing from clouds to ground. Those particles are charged differently. So some are positively charged, some are negatively charged. Like charges, so if they're both positively charged, actually repel, so that forces them apart, and unlike charges actually attract, so it brings those particles together. So when we talk about a flow or an ordered movement of these negatively charged particles, we actually talk about it being electric current, so it flows. It's a flow of electrons. From, in this case, if you've got a battery, the battery causes that flow of electrons from the negative terminal to the positive terminal, and that causes, in a torch, it causes the light bulb to light when you switch it on, and when you switch it off, it stops that flow of electrons. That ordered flow of electrons, that electric current, is measured in what we call amps or amperes, and the symbol is I. And I'll go into that in a sec. The battery is a source of these electrons through a breakdown chemical reaction, and the battery, because of this flow, it's actually a force. So we call it an electromotive force. And we don't tend to call it EMF very much these days. We call it a voltage. So a voltage is that electromotive force that pushes those electrons round a circuit. So we've got current, which is the flow of electrons, and we've got voltage, which is the electromotive force to push those electrons around the circuit. Voltage is represented by V or E. It's in your exam papers it's E. So yeah, that's the symbol, if you like, for voltage. E as in electromotive force. Now a higher voltage equals a higher pressure. So if you've got a much higher voltage, it's actually going to push those electrons around the circuit much faster. And excessive voltage, so very high voltage, or voltage of the wrong polarity, so if it's the wrong direction, can actually damage electronic circuits. Any questions? Okay, to get that flow of electrons around a circuit, we need conductors. So, and the definition of a conductor is it only needs a really small pressure to actually move those electrons through it. Good example, things like aluminium and copper. The wiring in your house is copper, and most of the circuits in electronic equipment is copper. So it allows that flow of electrons really easily. The opposite to that is insulators. So, and the definition is you need a very high electrical pressure or voltage to actually get the electrons to move through them. And usually when you have such a high voltage to try and move it through, you actually damage the material doing it. And a good example is plastics, ceramics, porcelain, glass, etc., etc. So, now another concept you need to be aware of. That flow of electrons, if it is all in one direction, what we call it is direct current, or where electrons flow in one direction, and direct current usually comes from something like a battery or a power supply. A good example of direct current is you've got 12 volt battery in your car, that's 12 volts DC, we call it direct current. Whereas there is another concept which is alternating current, which is what comes out of your mains outlet. And all that means is that the flow of electrons changes over time. It goes positive for some of the time, goes negative, and keeps doing that. It alternates from one polarity to another. And it's usually generated by something like we call an alternator, which is just a generator that alternates the current in one direction and the other. And a good example is the 240 volt mains. So, okay. The amount of electrons that we can push down a wire is dependent on how thick the wire is and obviously how long the wire is. The thicker it is, the less resistance to that flow there is, and the longer it is, obviously the greater the resistance to that flow is. So, however, if you increase the pressure or the voltage level, you can actually push more electrons down that conductor. So a good analogy here is if you think about water flowing through pipes, actually the formulas that are used to work out the flow through pipes is actually exactly the same as the flow of electrons through conductors. Surprise, surprise. So good example where, make the pipe bigger, you can push a lot more water through it. Make the conductor bigger, you can push a lot more electrons down it. Now, we talk about resistance here. Resistance is a parameter that we can measure, and its symbol is R, and it's measured in what we call ohms. So it's a certain number of ohms, and the actual formula that we use, it uses R. The actual symbol for it is the omega symbol, the Greek omega symbol. And resistance is defined as the opposition to that flow of electrons or that current flow down a particular conductor. Resistors, and resistors are in electronic circuits, exhibit resistance of a certain value, and they're colour-coded. You don't need to know the colour code as a foundation licensee. If you go to standard and advanced, you do need to know the colour code. They're usually very small components, so in that sense what they do is they have a particular colour code that they use so that you can, they're too small to write a number on, so you put coloured bands on it. And the size of the resistor, because a resistor resists the flow of electrons, but in resisting it has to convert that energy into something else. And so what it does is converts it to heat. And so in certain situations you need bigger resistors that get hotter, and so size actually relates to the amount of heat or power dissipation that they can take. And this is a great little aid memoir. Voltage is pressure, so it's pushing the current or the amps through a particular conductor here, and the resistor is causing that the current to slow down or resist that flow of electrons. So it's a good little symbol to remember. Now, this is as hard as the maths gets in foundation licensees. For foundation licensees, you need to know Ohm's law. This is a great way of remembering Ohm's law. The triangle, and the way we use the triangle is we've got voltage, we've got current, and we've got resistance. if you cover up the one you don't know, so if you're given in a question a voltage and a resistance and it's asking you what the current is, the way you use this triangle is you cover up the one that you need to know, and what it's telling you is the formula to work out the current is the voltage divided by the resistance. And same with if you're given voltage and current and you need to know the resistance, same story. It's the voltage divided by the current. Now, if you're given the current and the resistance and you need to know the voltage, what it's telling you on the triangle is the current multiplied by the resistance. So that's divide and that's multiply. So one of the things in the exam is you're given a blank sheet of paper that you can scribble on. You can scribble to your heart's content on that. One of the key things is if you don't remember Ohm's law very easily, is scribble the triangle on the paper, and then you can work it out. So, and this is what it looks like in formula, rather than the triangle. So, current, voltage divided by the resistance. Voltage is current multiplied by the resistance, and the resistance is the voltage divided by the current. So, any questions? And the sort of question you'll get in the exam is, you'll be given, for a voltage and a current of X, what is the resistance? And there'll be four different answers that you've got to choose. So, and I think one of the example questions we've got that. Now, the unit of power, so I talked about that power dissipation in resistors, is the watt. So, and a good example is the urn has a rating on it of, I don't know, 1200 watts. It tells you that it is able to dissipate 1200 watts or provide 1200 watts to boil the water. The definition of it, a watt is 1 volt, so that's our pressure. 1 volt applied to a circuit causing 1 amp of current to flow will cause 1 watt of power to be dissipated. And a good example here, the reason we put this diagram in is out in the countryside you'll see those huge big electricity pylons, which is taking electricity from power stations out in the middle of nowhere back into the city. The power companies, so that they don't lose a lot of that power in unnecessary ways, what they do is they raise the voltage, so they raise that pressure up to really, really high pressures, but really, really low currents. And the reason why those pylons are so high is because of it's very, very high voltage. They need to get those conductors away from everything, so they make them very high. And you'll notice the insulators on them are very long, big ceramic insulators. So as it comes into suburbia, what they do is they drop the voltage down, and what that does is drop the voltage down, but they raise the current. So by the time it gets to your house, you've got 240 volts coming out of your socket. So it's reasonably low voltage. It's still scary voltage, but it's reasonably low voltage, but reasonably high current. So they're not losing a whole lot of power along the way, and they're able to transmit that power or transfer that power long distances to do that. So it's a good example of using Ohm's law to actually bring the power into suburbia. Now, power, you don't actually need to know all of these formulas, but there is one key one that we need to be aware of, and power equals voltage times the current. So if you know what the voltage is and you know what the current is, you can actually work out what the power is. So And a way of defining it, if you like, is power is the rate at which energy is converted from one form to another. And a resistor is a great example here, because a resistor has a rating on it, and it says the resistor is a 1 watt resistor. So that resistor can actually take 1 watt of power before the resistor potentially fails. The resistor gets hot, and that's the transferring the current, the resistance to that current flow into heat. So it's the rate at which energy is converted from one form to another. But it's, in this case, you don't need to know all of these, but that one you need to be aware of. Any questions? Now that's as hard as the maths gets. If you're comfortable with that, okay, we're right. If you're not, then please speak up or come and see us. Now, there's another type of slide in these slide packs, which is, it refers to practical. So we just give you a few hints and then we'll revise this at the very end of the slide pack. Some of the symbols we need to know. So what I will actually be doing is holding up and giving you ones that don't have the names next to them and asking you to tell me what they actually represent. In a circuit diagram, these are the sort of symbols you actually see to represent different components in the circuit diagram. So there's the wiggly line, or a square, is a resistor. We've got a switch, an antenna, an earth, a microphone. We've got a lamp, fuse, battery, a single cell. So a battery is made up of a whole bunch of cells. So that's how those two link together. And then the one at the top, which is a speaker. So, and we'll revise those before we go into the practical. Now, we use very large numbers and very small numbers in amateur radio and electronics. If we were having to write out all the zeros each time that we use these numbers, it would drive us crazy. So what we use are some prefixes around very large numbers and very small numbers. The ones that we are concerned about in the foundation license assessment are the ones in the middle. You don't need to know all of these, but the mega, kilo, milli and micro. So mega is a large number and it's a million. So it's 10 to the 6th, there's 6 zeros after that. Kilo is 1,000, and think about kilometres. Kilometres are 1,000 metres. So, okay, you can translate that, that's good. Milli is 1,000th, or 10 to the minus 3, and micro is 10 to the minus 6, so a millionth. And some good examples are very high voltage. We don't say 22,000 volts, we say 22 kilovolts. Just a short way of saying it. Go in the other direction, 2 millivolts, or 2 millivolts here, is 2,000ths of a volt. Just a very simple way of representing it. 22 k ohms, or 22 kilo ohms, 22,000 ohms, so that's a resistor value. An even bigger resistor value, 1 mega ohm, so mega ohm or mega ohm is 1 million ohms. 15 milliamps, or 15 thousandths of an amp, and even smaller, 120 microamps, or 120 millionths of an amp, really, really small. So, any questions, concerns about using that? What a sort of example question would be 22k ohms represents, and there would be 4 which would give you, and it would be 22,000 volts, or 22,000 whatever the units are. in the question, and which one's right. And it would give you 22 million, 22,000, 22 thousandths, and you'd have to pick the right one. So that's the sort of question that would be in the exam. All right, frequency. Now, we talk about frequency. It's measured in hertz, which is the number of cycles per second. The number of, and we're talking about alternating current here, so it's going positive and negative. And it's the number of cycles of alternating current per second. So a good example is, we talk about this being 240 volts at 50 hertz. All that means is 50 hertz means that it's alternating at 50 times a second. So, and that's at mains voltage. What we talk about when we talk about radio frequency is it's up in the many thousands or millions of hertz, so it's doing that many times. Audible frequency range. So the audible frequency range is something like 20 hertz to 15 kilohertz, although the top end, as you get older and older, gets lower and lower, because I know mine's really low. It's probably all those concerts I went to and all those headphones that I wear. But so we talk about it being 20 hertz, which is really low frequency, up to your mosquito sort of frequencies. That's 15 kilohertz, really high. The voice range, when we talk about, and radio telephony is just voice on the radio, is something like 300 hertz, so it's a little bit higher. 300 hertz you'll be able to hear or feel, and up to 3 kilohertz. So that's the sort of voice frequency range that we're talking about there. And this is, we talk about that being alternating current. So alternating current has a frequency, which is how many times it alternates. It has a wavelength. So over time, one oscillation, so one positive and one negative, that happens over a particular time, and we can measure the wavelength of that and the period of that, so the actual time that it takes. And it's one cycle. It's what we talk about, one cycle as a positive and a negative. And what we can then do is, because we know that the speed of light is constant, there's a little formula that says wavelength, and that's the symbol for wavelength. The wavelength is the speed of light, which is a constant, divided by the frequency, in this case megahertz, to give us meters. Now, any questions about that before I head on? You don't have to know that formula, but if there's a question around this in the exam, you're given this chart. This chart's really handy because it gives you frequency on one axis and wavelength on the other axis in meters. And if you might be asked, okay, for a frequency of 20 megahertz, what's the wavelength? The way you use the chart is find the frequency here, go across to the red line and then come down, and that would be 15 metres. And you can use it in reverse as well. So if you're given the wavelength of 20 metres, which is one of our amateur bands, 20 metre, we talk about operating on 20 metres. So we find 20 metres, we go up here and we whiz across here, and it's about, in this case, 14 megahertz or 15 megahertz. So that's that formula in a graph, in a chart. So if there's a question in the exam around wavelength and frequency and conversion, the chart will be in the exam. It'll actually be on the exam that you can use. So you don't have to worry about it. You just need to know how to use it. So are people comfortable with that? Okay, let's go up in frequency a bit, past the audible, the audio. Radio frequencies, we split up into 300 kilohertz to 3 megahertz, 3 megs to 30 megs, and in fact each of those lines up there on that chart match these. There's a few down the bottom. There's a few up here and there's a few down here, a few higher ones and a few lower ones. So that's how we split up. And you'll notice we talk about HF, we talk about VHF, UHF CB. 27 meg CB is HF. It's in the HF band. So, and then there is an area in the middle called very high frequency, or VHF. Okay, questions. Electric current is... Anyone want to have a guess?
See.
Movement of electrons from negative to positive. Spot on. You can discount most of the other. Electric current is a flow of electrons. Remember flow of electrons, and that helps you out. The opposition offered to electrons, that's resistance, the rate at which is changed from light energy. Yeah, no. Perfect. Good conductors are D, copper and aluminium, well and truly. The B and C are all insulators. A, they throw in silicon and germanium are actually what we call semiconductors. This is what transistors are made from. So they throw that in to really go, oh, yeah, okay, right. Now, here's a good example of Ohm's law. If 10 volts is applied to a circuit consisting of a resistance of 5 ohms, so what you're given is you're given E and you're given R. E-I-R, so it's E over R. So it's 10 divided by 5.
2 amps.
So
2 amps.
it's 2 amps. That's the sort of question you'll be given. 1,000 volts is often represented as
Kilovolt.
1 kV. Well and truly. And in fact,